Sound waves are longitudinal waves that travel through matter. These are the most common types of longitudinal wave you'll meet at GCSE, so it's important to understand how they travel. Here's a simple representation of this. These circles represent air molecules a sound is travelling through. The sound causes the molecules to vibrate back and forth, which transfers its energy forward but doesn't cause the air to move overall. It's important to remember that sound is a mechanical wave, meaning it needs some form of matter to travel through. This is why no sound travels in outer space, which is a vacuum. But while sound usually travels through air, is it the only way sound can travel? What happens when it reaches a boundary? Well, the sound wave can be transferred from one medium to another. Sound waves can travel through any matter which can vibrate. This includes solids, liquids, and gases. Though sometimes the sound will be reflected or absorbed at certain boundaries. Let's focus on sound transmitting and being transferred for now, with an example of how sound can be transferred from a solid to a gas. Here we have a tuning fork, where the metal in the forks is a solid. When we strike it, it causes the forks to vibrate as a sound wave forms in it. But how do we hear this sound? It has to leave the fork and reach us somehow. As the forks vibrate, they disturb the air around them. The vibrations from the fork are given to the air nearby. This means the sound wave has been transferred from the solid fork to the gaseous air. The air can then transport the waves to our ears so we can hear the sound of the fork. Let's quickly look at some more examples of this. Many musical instruments and other devices that create sound work by creating vibrations which transfer to air. For example, we pluck guitar strings to make them vibrate. These vibrations are transferred to the air inside the guitar, causing a sound wave to be sent from the guitar and carried by the surrounding air. Or we can create vibrations in the air directly. For example, a trumpet is designed so that when we blow air into it, mechanisms make it start vibrating as it passes through. This air carries a sound wave as it leaves the trumpet, which is transferred through the surrounding air. We could also use a speaker to take an electrical signal and use it to create a sound wave. The signal causes these drum-like diaphragms to vibrate. The properties of these vibrations are determined by the type of signal received. The diaphragm is designed to make the air around it vibrate, transferring the sound to us. You won't need to be able to recall these exact examples for your exam, but you should be able to explain how we hear a sound from a given device because it transfers vibrations to the surrounding air. Now let's take a closer look at what determines the properties of the sound. The amplitude of the waves determines the volume of the sound. The volume could be changed by, say, plucking harder on a guitar string or striking a tuning fork with more force. Let's see why. Here we have the oscilloscope readings for two different sound waves. The y-axis represents the displacements caused by the waves, and the x-axis represents time. The reading on the left is for a low-volume sound, like a whisper, while on the right we have a high-volume sound, like a shout. As we can see, the louder sound has larger displacements and a greater amplitude. This means that the wave is carrying a larger amount of energy than the quieter sound wave. This won't come up on your exam, but it is useful for helping you understand how sound and waves in general work. We can also use information about the wave to describe the pitch of the sound. The frequency of the waves determines the pitch of the sound. Most instruments or devices which create sound have mechanisms which change pitch. Most instruments or devices which create sound have mechanisms which change pitch, like different strings on the guitar or how the diaphragm of a speaker beats. Let's see what exactly this changes. Here are two more oscilloscope readings. Remember that the horizontal axis represents time, so the fact that we see more wavelengths in this image means that the vibrations are happening more rapidly. So this is a wave with a high frequency. The fact that this wave has a low frequency means it's for a sound with a low pitch, like a bass guitar. Then the high frequency wave is for a sound with a high pitch, like a whistle. The fact that pitch is related to frequency also explains why the pitch of a recording changes as we speed it up or slow it down. Again, this is some detail you won't see in an exam, though you do need to understand that the frequency of a sound wave greatly affects the type of sound we hear.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy-to-follow videos, and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!